Let's find the Fourier transform of this signal x of t, which is e to the negative a absolute value of t. By definition, the Fourier transform of any continuous time signal is the integral from negative infinity to infinity of that signal times e to the negative j omega t dt. Substituting our x of t, we get this integral. Now, to get rid of the absolute value, recall that it's a piecewise function. The absolute value of t is just t for positive values and negative t for negative values. We'll use this to split the integral over two regions, negative infinity to 0 and 0 to infinity. We'll use laws of indices to simplify the integrand in each case and factor out a t. And now we're ready to integrate. The exponential part will stay the same for both, but we'll just have to divide by the coefficient of t in each case. So this is the result. Now note that when we say infinity or negative infinity in the bounds, technically we should be taking a limit, as we would learn in a Calculus 2 course, because this integral is improper. But in an engineering course, this is just implied, so you don't explicitly have to spell out the limit. This is just implied as part of the process. So, applying the bounds, we get e to the 0, which is 1, and e to the negative infinity, which is 0 in the limit. Similarly, we'll get this result for the second integral. And now we'll simplify and get the sum of these two fractions. Now we may want to stop here, but the fact that the denominators are complex conjugates inspires us to try and have a common denominator and add the fractions, hoping for a nice simplification. Doing so, we'll get a plus j omega plus a minus j omega in the numerator. So you can see that the j omega term cancels out. The result is 2a over a squared plus omega squared. What's nice about this result is that it's purely real because there's no element of j anywhere in the expression. So that's the final answer. The Fourier transform of this double-sided exponential we started with is 2a over a squared plus omega squared.